So please welcome our next speaker, Alexander Færøy, who will be talking about the Tor ecosystem.
Thank you. Just adding a bit to the information that was just said. If you want to participate in the Hacker Jeopardy, send an email to info@bornhack.org if you want to participate as a team. Okay, so this presentation usually takes an hour and a half, and I need to squeeze it into 45 minutes, so we're going to rush through some of the parts, but feel free to ask questions afterwards. My name is Alex. I work for the Tor project, and I've worked there since early 2017. I've always been very interested in distributed systems, and before Tor, I was working for a small startup in Denmark, in Copenhagen. And I'm one of the core organizers here for BornHack. So what is Tor? I think most people in this room probably knows a bit about Tor, but it's an online anonymity and censorship circumvention tool. It's free software, which means that you get access to the source code, you get to inspect it for bugs, you can participate in the development. It's also an open network in that everyone can run nodes that participates and acts in the same way as other people who run nodes. We have a pretty nice community of both researchers, developers, users, and then we have the relay operator community, which is the people who are running the network. The network is operated by volunteers, like probably people in here, run some relays, and is separated from the Tor organization itself. We are also a US 501c3 nonprofit organization based off in Seattle. So if we look a bit at the history in this space, in the 1990s, the whole onion routing, which is what essentially Tor is doing, started being interesting for researchers. In the early 2000s, Tor was developed together with the US Naval Labs. And in 2004, we got a sponsorship by the EFF to sort of be an official sponsor. And in 2006, Tor incorporated and became a nonprofit. In 2007, we expanded to also have anti-censorship and not just anonymity. And that's something this talk is also going to relate a bit to, because that's something we've been working a lot on in the past 2 years. In 2008, the Tor browser came, when people started realizing that just having network anonymity was not enough. We also needed to look at how the browsers behave on the network and different fingerprint methods that you could get from, for example, JavaScript. In 2010, we saw a big spike in both popularity and interest in Tor with the whole Arab Spring. In 2013, in the summer, we saw the revelations by Snowden, which also gave a lot of attention to Tor. In 2018, at the end of that, we created a new team, which is our anti-censorship team, to have a dedicated team to work on the whole issues with countries that apply censorship for people. When we have these anonymity networks, it's hard to just measure things like we usually do with different kinds of software. So we used to say that we have around 2 million daily users, but a recent research paper indicates that it might be closer to 8 million. But we're trying to be a little bit conservative, so it's probably somewhere in between there. The primary product that we make that people use when they go to our website and download the product is a web browser that we call Tor browser. It's based off a Firefox release, the extended support releases, and it ships with all the components inside, like Tor itself, which is the thing that does network anonymity on the network layer. And the browser then has a lot of patches on top of an ordinary Firefox to provide different kind of metadata resistance and fingerprinting options that are disabled. In 2018, we began development on porting the Tor browser to Android. Before that, a friend group we have called the Guardian Project maintained a browser called Orfox. But we decided that Android was a high enough priority that it should be developed in-house and be maintained by the browser team inside the Tor project. So this is available now on Google Play, for example, and I believe it's also available on F-Droid if people want to try it out. And if you see any bugs, please report them, because this is still in early development. So before we begin with diving into all the Tor things, we're going to look a bit at like threat modeling, which is a good start for talking about and reasoning about these anonymity networks. This does not specifically relate to Tor. It can be applied to other anonymity networks, but we're going to look a bit at what can the attacker do. That's essentially the question we want to see. So one thing the attacker would be able to do is be monitoring. We have two entities here. We have Alice, we have Bob. And then we have an adversary, which is the sketchy-looking guy. In most cases, Bob is a web server somewhere, or a chat server, or whatever, and is not actually a person. One problem we can have is that someone is monitoring Alice's computer, or the network she's on. This could be like a partner that's monitoring the traffic that's going on, or it could be Alice's ISP, or the state that Alice is in. So the adversary here can monitor access into the anonymity network. Another option could be that the adversary control parts of the network. We're going to come back to that one later. And there's of course also the option that the adversary is monitoring Bob on the other end and can see the traffic coming out of the anonymity network and is reaching the endpoint, which is Bob, which is most likely some kind of web service. And finally, there is the option that the adversary is actually Bob, but that one is more difficult to deal with. When we go out, we talk a lot about, we get a lot of questions about anonymity versus encryption. And anonymity is not encryption in itself. Encryption just protects the content. But it does not protect various signals, such as, for example, there has been a TCP connection between two endpoints. When you visit a website over HTTPS, you might learn data about that you've made the connection, how long did the connection take, how much data was transferred over it. And this is the data we call metadata. That is the data about data that is happening on the wire. And this is one of the things Tor tries to protect you against by, for example, adding padding and so on. We know from Michael Hayden, who very openly said that they kill people based on metadata's information. So when we go out and talk with people, it's various different entities, and they all see Tor as a good thing for different reasons, and the anonymity for different reasons. For governments, it's usually about the traffic analysis resistance. And for the human rights activists, this is where the anti-censorship part comes in. It's more about reachability, like being able to access information, being able to post information. For like ordinary citizens, I would think that applies for most people in here who are using Tor occasionally. It's about privacy. And for businesses, it's usually about network security. So before we begin with diving into Tor, we've looked a little bit now at the threat modeling. We're going to build up sort of a simple model for what it is that we're doing. This design we have here, where we have different entities that are communicating with each other using a single relay. This could, for example, be a VPN service. It could be like an SSH host. It could be like whatever, some kind of proxy. Either they encrypt information like end-to-end to each other, or they encrypt with the key to the relay, which is what most VPN providers do. Here is, of course, the problem that the single relay is a sort of a fat target. It's a single point of failure. If this one is evil or malicious in any way, you lose a lot of the safety from this, from using this. And even if the actor itself is not malicious, it could be that because it's such an interesting single point of failure, it might be that someone is monitoring these things coming in and out of the relay. And because of all the metadata we were talking about before, it becomes pretty trivial to sort of bridge what's coming in and what's going out. So instead, with the Tor design, what we do there is that we, instead of having a single point of failure, we add multiple relays so that no single relay can betray Alice in this case. So when Alice wants to make a connection through the Tor network, she picks a path. It's very important that it's Alice who decides the path through the network. She picks 3 relays, R1, R2, and R3, before she finally asks R3 to connect to Bob. This happens by Alice establishing a session key with R1, asks R1 to extend to R2, and asks R2 to extend to R3, and then finally make the TCP connection out to Bob, which is most likely is like a web service somewhere. Because of this, the R1 node we have will know that Alice is accessing the Tor network, but does not know what Alice is, that Alice in the end is contacting Bob. R3 knows that Alice comes via R2, but doesn't know about R1, but knows that Alice is connecting to Bob. That's sort of the idea here, that they have to cooperate to be able to betray Alice. So as mentioned before, it's an open network. It means that everyone in here can run a relay. I know there's people in here who are running very big relays, and thank you for doing that. We have somewhere between 6,000 and 7,000 nodes right now. It's going up and down every now and then, and sometimes we do various campaigns to get more people to run these relays. There's 9 sort of special nodes in the network called the directory authorities, which is operated by various trusted individuals around the organization, which is the nodes that decide which other nodes are part of the network. Like, they vote occasionally about these things. And we have something called a bridge authority. I'm going to return to that afterwards. The IPv6 story is something many technicians ask us about, and we are right now in a sort of in a project where we are trying to get more people to run IPv6 relays. So if you're running a relay, please enable IPv6 on it. We cannot just switch over to just using IPv6 if some of the network is using it, because we want the entire network, like every node should be able to reach every other node, which is an important property of the system. This graph shows the bandwidth inside the network. We have 2 lines here. We have the advertised bandwidth and we have the bandwidth history. The advertised bandwidth is what the relays think they can run, and the bandwidth history is where they report how much traffic they've been crunching through recently. And we can see that there should be around 300 gigabits in the network, and we're using around half of it at the beginning of 2019. And this curve is just continuing for the rest of 2019. One of the very important parts about Tor is that the safety comes from diversity in the network. It comes from diversity of relays, in that it's multiple different people who are running them. They're running them on multiple different operating systems. And because there are multiple different individuals, you will have to get some of them together to be able to attack the users who are using this system. One of the research problems we have is that we don't really know how we measure this diversity property over time. We just know that it's something that is important for us. And of course, another thing is that the diversity of users is important. If it's only like sketchy people or only bad stuff that's going through, then this system doesn't work. It's very important that like normal people just use it for web browsing, so that the system is sound. And that is, amongst other, for example, if there's 50,000 users in Iran who's using it, it means that most of them are most likely like just normal citizens and not government people or anything. We recently did a survey where we asked different people on our blog to tell us a bit about what it is they use Tor for in various situations. Here we have a political activist who's part of a semi-criminalized minority who participated in public debates in their location, and Tor allows them freedom to publish the messages to the world without being affected by it. Another one we have is a doctor in a very political town who have some clients. As many of you probably know, doctors are also using the internet to look up diseases and so on. And this one don't want the people to be able to, who might be monitoring him, to be able to correlate who has recently been visiting and what kind of diseases they might have. The number of relays we have is, as mentioned before, is going a bit up and down. Right now we have somewhere around 6,500. I think it's closer to 7,000 right now. The bridges is ordinary relays that are used as entry points into the network, but they're not part of what we call the consensus. So you can always download a document saying all the nodes that are in the Tor network, but the bridges won't be listed there. Bridges are used by people, for example, in China, Iran, and so on, who gets information about these nodes on the non-censored part of the internet and will be able to enter the Tor network via that, because it's very easy, because the because of the knowledge of all the nodes in the Tor network is public, it's very easy to just block all the IP addresses that are part of the Tor network. Bridges is something we also need people to run. We have fewer bridges than we have relays, so if you have the capacity to run a bridge, please do so. I talked a bit about diversity before of the platform, of the Tor system. One place where we are not very good at being diverse is when it comes to the operating systems that are running these relays. We are very much a Linux project. As you might be able to see on the curve, in early 2016, the BSDs took over from Windows as sort of the second most popular platform to run relays. So we could really use that people run it on something else than Linux. It would be very bad for the network. If there is some very serious security issue in Linux, then the network would be impacted by that. The reference implementation of Tor is written in C. We are very aware of all the problems that are around writing things in C, that you have the option of shooting off parts of your body every time you're writing a line in that language. One thing we're experimenting a bit with right now is using Mozilla's Rust programming language to write small components in Rust. Rust has this very beautiful feature where memory unsafe code is within a block that is called unsafe, which makes it much easier for people who are reviewing the code to reason about what the code is doing, because they can assume that it's memory safe by default. And if it's memory safe, then we are hopefully avoiding a lot of catastrophic security issues. We try to follow these best practices for code management. We have very high coverage for our unit tests. We do integration tests. We have a tool called Coverity, which is it's a hosted static code analyzer, which comes with information about here you're going to have a memory leak, here you're going to have some security issues, and so on. And we take those very seriously when they come in. We have people on the team who are rotating and taking over the responsibility of these weekly. We also have a very strict code review policy. Most of us in the team who are working with the Tor source code do not commit directly to the tree. We have some people who can merge patches. And we have a strict policy that the person who writes the code cannot merge it, and they cannot review their own code. So we usually need 3 people before code gets into the tree. This makes development a little bit slower, but it's nothing compared to already being in the C programming language, which also takes a long time to write stuff in. We do specifications for everything we do that touches the network, and we have a special repository for that you can see on gitweb torproject.org/torspec. This is where we document, for example, cryptographic handshakes, how the network protocol looks, and before we start implementing anything that has to do with the network needs to have a proposal that's being discussed, sometimes in a long time before we actually start implementing it. This is a screenshot from our website. In 2017, there was this tool called PVS Studio that tried to do static code analysis on the Tor code base, and he didn't find anything, which I think was very cool, but it's a very nice tool as well to apply to your C code if you want to play around with it. Any questions about this thing with the implementation and so on? No, doesn't look like it. Great. Another thing we have is onion services. It is one of the things where especially Danish newspapers are very happy to have like a fact box on their website telling about Tor every time there is some bad stuff going on the dark web. This is the onion services. It's a special use domain name. It was defined in RFC 7686. It allows servers to be anonymous. So it's not just the client who are able to hide themselves, but we turn sort of the server connection into also being a client into the network. And then you can rendezvous in the middle of the network and do connections there. It was introduced all the way back in 2004 and was written by Roger Dinkeldine back then. And one of the cool things about this is that the different relays we have, as you saw with the R1, R2, R3, we usually also call them the guard node and the middle node and the exit node. The exit node, which is R3, is we have less resources of those because they're the one who sort of also gets abuse information, gets like abuse contact because it's where the traffic goes out. So it requires a bit more of you as a hosting provider to be able to host the exit nodes. But the cool thing about onion services is that they stay within the Tor network, which means that everyone is sort of participating equally for those. One thing with them is that they are 16 characters long for the old version of it, the thing we call version 2. And for version 3, they have 52 characters, which is very long domain names, and it's sort of random characters, because it's the public key that we store directly in the host name. One of the open research problems we have right now around that is how do we handle these long addresses, because nobody is able to remember, or hopefully not many people are able to remember these 52 character sequences. In practice, it's very difficult to see here, but you might be able to see that this is an onion version of the torproject.org website. It's basically just like a normal thing that you're just using it via Tor, and you are only able to access these onion addresses via the Tor browser, or via Tor itself if you're using it, for example, to connect to the BornHack IRC server has an onion address. One of the cool thing about the onion services is that they're self-authenticated because we have the public key in the name. We know that we are communicating with the right host because we can like ask them to sign something for us and see if it checks out. They have end-to-end encryption. It allows people who are behind these NAT routers at home to be able to host things if they want to do that, because the server itself is connecting into the Tor network, and the client is also connecting into the Tor network, and then they meet somewhere in the middle. It supports Unix domain sockets as well, which is a very nice feature for trying to isolate a bit the attack surface of various sites. So you can, for example, if you want to run an Onion web service, you can ask Tor to connect to a Unix domain socket on the file system, and then have Nginx provide the other end of the socket, so that you can have an Nginx which does not listen on TCP ports. Onion services is still a very little amount of our traffic. If you remember the chart from earlier, we were looking at that we have around 150 gigabit per second of traffic going through from the history. And what we see here is that around 1.5 gigabit of those are Onion traffic. So it's around 1% of the current traffic. The dark web, which is something we think is a bit silly, but this is the way it's often depicted in media. And it's sort of mixed a bit between like online criminal activity, for example, drug sales, weapon sales, all these kind of things. They're usually unindexed, which means that you cannot find them via Google or Bing or whatever you're using. And then some of them are running via an Onion service. One of the things we're not fully sure is like which one of these is actually the dark web. And in reality, it's probably sort of the intersection of all of these three. And of course, scale also applies here. We know that there are not that many Onion addresses, and so the dark web must be somewhere around here. The biggest of these so-called dark websites is, ironically enough, Facebook.com. Facebook started in 2016, I believe, to operate an Onion version of Facebook. They did a very cute thing with their Onion address is Facebook core wwwi.com. And they wrote this press release after they did it, where you get access to Facebook's core World Wide Web infrastructure. And a lot of people were panicking, because if they had chosen the public key to the point where they could just generate this, they would have compromised the security of the whole thing. But it seems like they just generated a ton of keys, and then they wrote the press statement after they had found one that they could spin this up on. They announced in 2016 that they have around 1 million users each, I think it's each month, that are using it over Tor. I still sometimes hear a bit of stories that people have difficulties signing up on the service with it, but they're able to log in. If we look at the censorship angle to Tor, which is the part that we have a lot of focus on since 2018 again, is if we need to sort of have an idea about how this looks, it's usually that Alice will be in some censored region and they're trying to access information that are on the uncensored internet. In this case, Alice is unable to reach Bob. That is one of the scenarios. The other scenario is that Alice can reach Bob, but their connection is greatly throttled, so they don't get much data through. And finally, there are of course certain situations where Alice can reach Bob because the censor basically thinks that Bob is an okay person to be in contact with. This is how it looks in practice for many people who are seeing this. There's something a little bit disturbing about sort of the cartoonish style added to this, and even the one in the left corner has a small input field with like enter your name, your email, the blocked URL, and a small comment on why you were trying to access it. I hope people are not really following through with that. This, especially I think for the Danish people in the audience, seems this is not the kind of internet that we're usually interacting with. But in Denmark, we have the exact same infrastructure ready. This is the Danish version of this site. It says that you are on your way to access an illegal website, and that they are very willing to help you with finding the movies or series that you're searching for. Or if you're searching for books, music, or furnitures, then you can also get some information here. And the organization in the left of the bottom is the Danish Ministry of Culture. They also have a little label on this. The anti-censorship strategies that we look at is that, as mentioned before, that censors will apply censorship to nodes in the network to prohibit access to the Tor network. And every time we see that bridges becomes publicly known, like if someone shares them somewhere, they have a tendency to get filtered as well. So the solution is either to make it hard to analyze the traffic or make it hard to block the bridges so people can continue to access the Tor network through that. The arms race that exists in this can be a little bit stressful in that you might have something that works great for example, people in China one day, and then the next day it stops working. So one part of Tor we have done to make this a little bit easier for us, it's sort of a design part, is that Tor is able to use these things called pluggable transports, where you write two components. You write a sort of a server and a client, which takes Tor traffic and obfuscates it to the point where it's able to communicate with the server. And this allows various people who are like outside of the Tor project to work on different kind of implementations that they hope might work or experiment with getting to work in different censored areas. This allows for slightly more rapid development than trying to get something into Tor and having to write everything in C and so on. And it has the benefit that the protocol is also sort of a standard, so people can use it with, for example, their VPN tool or any other tools that basically speaks TCP connections and can take these streams and send through the pluggable transports. The most popular pluggable transport we have right now is the obfuscator or OPS4. It's the thing that that most people are using these days. It does some various things on the cryptographic part of the handshake, so that it tries to hide itself on the network wire, and you can also tune various timers for when they transmit and receive. A very interesting tool we have is called Meek. It uses a strategy called domain fronting, which means that you make a TLS. We exploit a bit sort of the centralization that is happening on the internet that I don't think anyone in this room is particularly happy about, but we know that there are like big cloud providers who are running large amounts of websites. And what we do is that we connect to their edge with a TLS connection where we set the SNI header to, for example, Instagram.com or something else that's hosted in that cloud. And then once we have the TLS connection established, we send an HTTP request inside of that with a different host header. So what the web server at the edge of these cloud providers will do is that they route us to the customer inside the network the host header and not of the SNI header. This is very efficient and seems to be working very well, because the game we start playing here with the cloud providers is that, or with the censors, is that if they want to censor access to us, they need to censor access for everyone who's inside the cloud. It's very efficient, but it's also very expensive. People who have seen AWS builds will know that traffic is not particularly cheap. And because of the way Tor works, the input amount of traffic is usually equal to the output amount of traffic. So it's very costly for us. There are some experiments going on right now with using eSNI, which is the encrypted SNI. I don't know if people have seen this. One of the problems with TLS, and one of the big discussions during the TLS 1.3 development, was that the SNI header, which indicate the host name that you're trying to use, remains unencrypted. So eSNI is a way to do that, but the current attempt to do this is made by Cloudflare. Seems to mostly focus on big providers who have a lot of domains on a set of servers. So what we can do there is also exchange information using eSNI. There's a project right now where the Guardian project is trying to give access to Wikipedia in certain censored areas with a small modification to a browser, where you can basically say, I want to reach Instagram.com, for example, and then you also have an extra URL, which is the site you actually want to visit inside, that is provided at this hosting provider that you're trying to access. Another option that we can use here is the various message queue services that many of the cloud providers have. They have a bit of a tendency that they use one unique host name for everyone who's using it. It's not hosted on your own domain name when you're doing development with it. Because of the price problem with Meek, one of the new things we've been doing this year is something called Snowflake. It's a slightly older design, but it's something we've spent a lot of time on trying to make nicer. What we do here is that we have the client, which is inside the red area, which is the censored area. What they do is that they use domain fronting to access what we call a broker. The broker has contact with what we call Snowflake proxies. These are small, sort of a little bit like a Tor node, but it's like a lightweight version of them that are running either in a web browser or as a web extension. So you can always have it running in your web browser. The broker is responsible for connecting these Snowflake proxies that are on the uncensored part of the internet with the user who's in the censored part of the internet, and they establish direct communication with each other using WebRTC, which is this peer-to-peer protocol that browsers are starting to provide for gaming and for media sharing, like doing conferences and so on. The Snowflake proxies that exist around that people are running on their laptop and so on uses a WebSocket connection to a bridge, which then gives them access to the Tor network. So everyone who have a web browser can sort of help people in these censored areas getting access to the Tor network. The game we play here is, of course, that we hope that WebRTC is going to be so popular that the censors are not interested in censoring all of WebRTC, but will have to start trying to attack this system instead. One part we haven't talked much about is to get information about where censorship is happening. We have a sister project called Uni, which what they do is basically they cover a lot of information about what's happening on the internet in various areas, and then they build reports like what's happening in around elections in Africa, or what's going on in Latin America, and so on. The way it works is that you run a small tool on your phone. It looks like this. It will do a lot of tests on the network that you're in and see various sites that are censored in this area, and whether, for example, if there's performance issues, if you're unable to reach instant messaging services. And then what they do when they're done with doing these tests is that they build like a data report and submit it to Uni, where they can then analyze what's going on with the internet around the world. It works a little bit like the RIPE Atlas project, if people are familiar with that, just with focus on the censorship part. They have a very nice website that you can check out. It's called explorer.uni.io. It shows a bit of information about how many measurements they have in different countries, and whether they identify vendors who are building some of these machines that does censorship in the areas. So yeah, go check it out. So Tor itself is not foolproof. You can do like operational security mistakes. Tor doesn't protect you. For example, if there is a prompt on a website asking you to enter your name, then you're not going to remain anonymous if you actually write your name. There can be issues with browser metadata fingerprinting. There can be browser exploits, and of course also traffic analysis. It's like a constant race we're in with trying to do better at these things, and researchers will come up with new attacks that we need to work with. So how are you able to help? You can either run a relay or a bridge, or you can teach others about Tor and privacy in general. We've seen a lot of these crypto parties in Europe over the last couple of years. Those are an excellent way to teach about Tor. If you're a developer, you can help finding and fixing bugs in Tor or implementing features. You can help if you're using some obscure platform. You can help with testing it on that. Or you can donate to us at donate.torproject.org. The donation money we get are really, really good because they allow us to work on whatever we want to work on, what we think is important, not what we're able to get funding for. That is it. Is there any questions? None. Great. Oh, there's one.
So you said that you are trying to make small modules in Rust.
Yeah.
Is there any plan for converting more of the core code base into Rust?
Yes. So the small modules we do right now is that we have a bit of a refactoring project going on right now where we have had this. Tor is a weird Unix application because it's a single binary that is essentially, it works as a client, it works as like a relay, it works as the directory authority that we only have 9 people running, it works as like the bridge thing, it's all these things inside one binary. So what we're doing right now is that we recently split the whole source code tree up to make it a bit more like we have sort of a framework we can work with and simplify things and testing things internally. And the way we deal with the Rust situation is that we usually have a C implementation of it, and then we have a copy of it in Rust. And then we try to do tests on, like cross tests on them to see if they behave and work in the same way. And we found some very interesting bugs in this as well. So it is essentially what we do is that we right now rewrite components that are in C also over to Rust. But we don't, right now, with the current releases that we have out, we don't require the people who are maintaining packages, for example, the Debian packages and so on, to build Tor with Rust support. But you can already enable, like if you say -- enable Rust, then you get the modules in Rust instead. Good question. Anything else? Cool. Thank you.